Oh, the recording's moving and I didn't notice. So, anyways, you'll see, and it may be mentioned in the video that one of the older ones, but I'll just make sure that I'll state it explicitly. It says here the average is the friction, and the difference is the tilt. That's wrong. The average value of them in the case of the level tracks is due to the average value is the tilt, and the difference, and actually the difference divided by 2 is the friction. So average is the tilt, and difference is the friction. And I'll show you here, I made up artificial data to just make absolutely certain. So I have a tilt, and these numbers are just accelerations. So when I'm going forward from gate 0 to gate 5, we call that forward direction. And so if I have a negative tilt, that means that it's tilted so that gate 0 is lower than gate 5. And if it had a positive tilt, then gate 0 would be higher than gate 5, which is what you do when you put those two little circular disc weight things and you lift up to one end. That's a positive tilt. Friction is always negative because it's always going to act against what's going on. So if you look at these two graphs, we have the forward direction up here, the reverse direction here. Now these graphs you know about from the other videos. And so you see here that when I let it go at top, it slows down. It's a negative acceleration. In fact, I have here, I took some data. So this is real data. And you see that when it's going in the forward direction, it has a negative acceleration total. And you see above in that graph, it's going slower. But you notice here, it's got a positive acceleration. It's also going slower. So what that tells me that is friction is dominating here. If there may be a residual tilt, and I would say that in this case, it's tilted. It might be tilted backwards. So we'll check it. I mean, I can see the answer in front of me, and yeah, it is tilted backwards. But let's just, for the time being, you see, in this case, the friction in both cases, when I'm going in the positive direction, it's slowing down, so that the acceleration has to be negative. And when I put it in the negative direction, it's also slowing down. And that means that it has to have a positive slope because it's in the opposite direction. And this is with the update when we were able to deal with the data when we're going from gate 5 to gate 0. So, but in principle, that shouldn't matter because we had the last video to set this up. So we sent it up. When we sent it up, it was a negative velocity. And it's a level track. We don't know. It looked probably the same, that it didn't change. But when we plot the data, at least I took this data, this is real data, we see it slowing down. So the acceleration is positive. And here, we sent it off with some certain velocity positive to the right. It's also slowing down, so that means that the slope has to be negative, and it is. And I would say then, because in this case, one is when the acceleration and velocity vectors are both in opposite directions in both cases, that means that what's doing this is friction, because friction is always pointed in the opposite direction of velocity. But now we want to go a little further, and so we want to get the averaged value. So I just simply made this little summary table here. And so that you notice that just equals here, the slope I got there, and this one equals the slope I got there. Then I take the average value of them, and it's negative, of course, because you see that negative, if I average together negative 0.8 and positive 0.6, the negative is going to win. And that's the average, is the residual tilt. And then look here, the difference, but it's the difference divided by 2. It's sort of like another kind of average. And we get negative 0.7. And look, you see what I did is I told it, I set this up. So you'll notice what these are from the equation, where you have like a x of 0, which is the 70, and there's a initial velocity, that's d16, 45 times the time, plus 1/2 at squared, and the a in here is a combination of the tilt and the friction. Okay. And so you can see now, I can put a 0 there. And I use these trend lines just because it helps me to see very quickly the changes. But you wouldn't see any difference right here. But I can go up to the solver. And let's see, this one's all set for the lower one. And we see the slope is plus 0.7. Even though the friction is negative, the slope value has to do with the direction of the velocity vector and the direction of the acceleration vector. And since I notice this thing is slowing down, that means that it's a positive slope because the velocity vector is in the negative direction. And then let's do on the upper one, sum of the residual squared. And now these two, slope and y-intercept, and solve. And notice now it's negative because it's slowing down once again. And again, the upper graph has a initial velocity of plus 45. The lower graph has an initial velocity of negative 45. So the upper graph, if it's a positive velocity and it's slowing down, that means it's a negative slope. That's what we see. So notice that I set the tilt to 0, and the average value shows us there's no tilt. This thing is perfectly level. And the only acceleration is coming from friction, and there it is. And the friction is the difference divided by 2. Pretty nifty, huh? So that's the exact right way to do it. All right. So let's take a look over to the tilted track. Now, of course, the tilted track is going to show us both of them with positive slopes. Because when we tilted up the end with gauge 0, and we've defined that as our positive direction because gauge 0 is at 70 centimeters and gauge 5 is 220, and if we send it from gauge 0 to gauge 5, it's moving in the positive direction, which also means it's tilted that way. So we're not surprised when we graph this all, we get a positive slope. Now, when we now do it in the opposite direction, so we're sending it up the hill, so we have a negative velocity, but we still have a positive slope because we didn't change the tilt, and it's very severe tilt. And we see we also get a positive slope, but it is not quite the same. So let's see what we have here. So we determined that, let's see, this is the tilt, this is the friction, and let's make sure I got this right. I don't know, oops. I got a toolbar you can't see. Yes, that's divided by 2. Okay. All right. So there's a significant amount of friction. And so let's see. It's a positive tilt. And so we would expect then that, but negative friction. So we'd expect both of them to give us an answer. If there was no friction, we would both give an answer that was a little bit higher than the acceleration of gravity. But when it's in the positive direction, when we're going downhill, so we go from gauge 0 to gauge 5, with the effect of friction, we expect to get something that's less than the acceleration of gravity. And then when we send it up the ramp from gauge 5 to gauge 0, we expect to get an acceleration that's greater than the acceleration of gravity. So let's see what we do. Well, first of all, we certainly see that the acceleration in the uphill is greater than acceleration in the downhill. So that's what we would expect with the friction. If there was no friction, they would both be the same. So now the question is, and I don't have this thing set up, but we can test it. At the moment, I'm using the average value here to get the measured acceleration. But for the moment, let's just use the upper graph. The upper graph is M12. So you see, we end up with something less, just as we predicted. And if I now say use the lower graph, we get something greater, just as we expected. So now, if we use the average value, then we can, all that's in there now is the acceleration due to the residual tilt. Because that way we eliminate the effect of the friction by taking the average value. And that means that it should be, if there's a residual tilt of plus 0.05, let's see if we, where is it? Average. What if I add a 0.05 here? So this will So that is 31.355. So we want to make it 0.05, right? Let me go back here for a second. 0.05. It's interesting. So that would make this 31.405. 31.405. Oops. 31.405. Oh, didn't work. No, then it's more of an analysis thing. I just couldn't help myself. All right, let's just stay on task here. And pause again for a moment because I want to make sure what I left behind. All right, so when I wanted to make sure what we need to have done before we go over the final analysis. So we have our process data. We have a graph. We have data points. We have a fit line. Then we do our residuals and do our residual squared. You don't have to be super quiet. This won't pick it up that much. And we got background. A lot of people in the room at the moment. The residual squared, and we're not worrying about standard deviation and such. And so then we have our sum of the residuals squared, and of course the sum of the residuals. This is all in the previous videos, huh? And then I just made this table here to make concatenate everything. And so there's the value. It's just that makes equals that. Escape equals the one down there. Then you have your average and the difference divided by 2. And then the tilted track, something similar. Notice I have the values I put here. We're measuring the height and the length. And it turns out then if you simply divide those two together, h divided by L is the sine, so you don't even need trigonometry. And you see here, well, this is a final result, but just look at that. So if you remember from the manual and the build-up, the acceleration of gravity is going to be the slopes, and the average slope we measured divided by the sine of the angle. And that gets us the acceleration of gravity, and then we have an accepted value right here. So we have the average value again. We see how it's copied down. Excuse me, copied down. And we'll discuss a little bit more. I've already discussed a little bit of the implications. I jumped the gun because it was just, it's just too interesting to me. I couldn't not look at it because I spent just today. I spent a couple hours making this because I had an idea in my head, and of course you always want to do a sanity check. And once I got this straight, then I knew how to tell you exactly how to interpret the level track data. Okay, so then this is what I'm going to ask you guys to hand in the night before we go in for our next lab, and we'll discuss it a bit in class. And then, this is pretty much done. And there's just a little bit more about analysis, and I'll make another video for that. All right.